Hi gang, I'm really sorry we had to cancel class today, but I just finished filming the demo lab, and as soon as I get it situated and organized and sent out to you, if y'all would go ahead and watch it and comment, that's all you're going to need to do for credit. Let's go ahead and start. So here we are, lesson 14, enthalpy, intermolecular forces, and states of matter. This is chapter 10, causes of change, sections 1 and 2. All right, let's see how we do. So energy transfer, heat. All right, now heat is the energy transferred between objects that are different temperatures. And heat energy is always transferred from a higher temperature to a lower temperature until an equilibrium is reached. If you remember, we've talked before about how, like, for example, if you're walking on a cold tile floor, the tile is actually the same temperature as the ambient air. It feels colder to you because your feet are touching it, and that heat, the heat from your feet, from your body, is moving into the tile, and that's what you're feeling. And energy, extensive, it's considered an extensive property, heat is. And what that means is the amount of heat depends on the size of the sample. Whereas temperature, we're going to find that's not necessarily the case. So if you had a tiny little candle versus a bonfire, one of them is going to give off more heat than the other, which makes it an extensive property. And then heat is always moving from hot to cold. And as you'll remember, especially those of you who were with us last year, that is the second law of thermodynamics. So then what's temperature? Temperature depends upon the average kinetic energy of the atoms. So that means how fast the particles within a substance are moving. And as I said, it's an intensive property. Temperature does not depend on the size of the sample. So you could have a marble-sized ball of lead, and you could get it to the same temperature as a car-sized ball of lead if you heated it up. And just so you know, if you want to get into a really awesome YouTube rabbit hole, there's a channel called, I think it's called Red Hot Ball of Lead. They heat up a tiny ball of lead, and then they drop it into all sorts of substances. It's kind of fascinating. Molar heat capacity. All right. Now, the energy as heat that's needed to raise 1 mole of an element or compound by 1 degree Kelvin or 1 Kelvin is the specific heat of a mole. And then sometimes it's shown as cm, so that's specific heat of a mole or molar heat capacity. And it does depend on the number of atoms present. And here's our friend Kelvin. There he is. So here is our equation for figuring out heat when it comes to molar heat capacity. Heat equals the number in moles times the molar heat capacity, which is in joules Kelvin per mole, and that is plus the times the change in temperature. So there it is again, and here's an example. How much heat is needed to increase the temperature of a mole of mercury by 10 Kelvin? Specific heat of mercury is 27.8 joules per mole Kelvin. So thus, we plug in our numbers, and we get this formula. And we can take out moles, and we can take out Kelvin, and we get that the heat is 1,390 joules. So if we want to find out the molar heat capacity, we need the mass in grams per mole times the specific heat, which in this case is joules per Kelvin grams. So using enthalpy, here's enthalpy, and it is how much heat and work was added or removed from a system. And it's the sum of a system's internal energy and the product of its pressure and volume. So we're talking about energy. We aren't talking as much about change. Enthalpy is where we talk about change. It's a state function. And this means that it's current value will only depend upon the final and initial values of heat and reaction, but not on the path or process that occurred for it to reach that value, which you probably noticed in the video I sent home for a homework assignment. So here's energy. It's the enthalpy of a system. It can be its total energy. And energy is only measured in joules, but enthalpy is measured in both joules and joules per mole. Enthalpy is also a form of energy, but energy exists as a state of matter. Enthalpy is always the change between two states. And energy can only be positive, but enthalpy can be both positive and negative. Oh, there's my light bulb. You can't see it behind my head. There you go. So molar enthalpy. And here's our equation for that. When only temperature changes, the change in molar enthalpy is represented by delta H, which is your change in heat. And then, oh, there it is again. And here's the whole explanation. Your change in heat equals your molar heat capacity times your change in temperature. So, for example, how much does the molar enthalpy change when ice warms from negative 5.4 Celsius to 0.2 Celsius? So what you do is you go ahead and you plug in. You're going to need your temperature final and your temperature initial in order to find out your delta T. And then you plug everything in as shown above. And when you work it out, whoop, I clicked, sorry. When you work it out, you get 1.9 times 10 to the second joules per mole Kelvin. So going over your notes and your homework, the total energy of a system is its enthalpy. The only way to measure energy is through a change. The molar enthalpy change is the enthalpy change of 1 mole of an element or compound. When a pure substance is heated or cooled but does not change state, the energy as heat is the same as the enthalpy change. Therefore, the molar enthalpy change is equal to the molar heat capacity multiplied by the temperature, or delta H is C delta T. A positive enthalpy change means that the change requires energy and that the process is endothermic. A negative enthalpy change means that the change releases energy or is exothermic. The science that examines energy changes that accompany chemical and physical processes is called thermodynamics. So solving the following problems, I'm just going to give you your answers so you can check them, okay? Did you get that one? I hope you did. In most chemical reactions, the enthalpy change can be measured in terms of energy in the form of heat released or gained during the reaction. A change in enthalpy in a reaction depends on many variables, but temperature is one of the most important. To standardize the enthalpies of reactions, data for reactants and products are presented at the standard thermodynamic temperature of 25 Celsius or 298.15 Kelvin. When a chemical equation is used in calculating thermodynamic values, coefficients represent moles of a substance. The enthalpy change in forming 1 mole of a substance from its elements is 298.15 Kelvin, and it's called the standard enthalpy of formation. So this was what I was going to do for y'all for your homework. I was going to give you these questions and see if you guys could answer them today in class. Whoopsie. But I'm going to let you go ahead and just look at this. And then that's it. I will send the lab out to you as soon as I get it. And again, I'm sorry I missed you guys today. You have a wonderful Thanksgiving.